Okay. Hi. Today we continue the topic we started last Monday, that is oscillations. And we considered oscillations of a body on a spring. And we obtained such an equation of oscillations: mass times acceleration plus the spring stiffness coefficient x equals 0, where x is the coordinate of oscillating body, and such coordinate that x equal to 0 No sound? No signal? Нет сигнала? Okay. I think there must be a signal now. Есть сигнал? Слышно что-нибудь? Okay. Okay, good. So the coordinate x in this equation of oscillations was chosen in such a way that x equal to 0 corresponds to an equilibrium position of the vibrating body. So if we divide this equation by m, we obtain x 2 points plus k divided by mx equal to 0. And we solved this equation, and it's better to say we found the solution by guessing and then substituting the solution into this equation, and we were sure that the equation is satisfied. We found the solution in such a way, as in such a function, that x as a function of t is some amplitude cosine omega t plus probably some initial phase, which can always be made 0 if we change the moment of time origin. If we start measuring time at a proper moment, then the initial phase will be 0. I will choose to denote this frequency of oscillations by omega 0, because today we will have another omega, non-zero omega, which will have different meaning. So this is the own oscillation frequency of the body on the spring, and this own oscillation frequency was found to be square root k divided by m. So that in this equation, x2 dots and the coefficient at the second term is omega squared x equal to 0. So this is an equation of harmonic oscillations. Such oscillations are called harmonic if they are described by either cosine or sine function. Sine and cosine is practically the same function from physical point of view, because the only difference is in its phase. And the phase can be changed by proper choice of time origin. So both sine omega t and cosine omega t are harmonic functions describing harmonic oscillations. Certainly there are many examples of non-harmonic oscillations, when oscillating body or vibrating body changes its position according to some different law which differs from cosine or sine. If the function x of t differs from harmonic function, then such oscillation is called unharmonic oscillation. And we will have an example. The vivid example is this here. I will show that this is an unharmonic oscillation which does not satisfy and does not obey the harmonic function of time. So if you consider some oscillating system, and if you come to such an equation, a differential equation describing this oscillating system, then such an equation where the coefficient at the first term at the second derivative is unit, then the coefficient at the second term will definitely be oscillation frequency squared. So there is no need to solve this equation many times. Each time you come to such an equation, each time you obtain this equation, you don't have to solve it, because this coefficient will immediately give you the vibration frequency. Now let's consider this case of a small body hanging on a thread. Such a pendulum is called an ideal pendulum. Sometimes people say this is a mathematical pendulum. Mathematical pendulum or ideal pendulum is defined in such a way that this is a small body hanging on a thread and capable of oscillating, provided the dimension of this or the size of this body is much smaller than the length of this thread. If the thread is much longer than the diameter of this body, of this ball, then this is a mathematical pendulum at a high degree of accuracy. It may be considered as mathematical pendulum at high degree of accuracy. However, if the diameter of the ball is large and you attempt to use such a large ball, then it will not be an ideal pendulum. It will not be a mathematical pendulum. It will be a physical pendulum, and we will consider such situation today. But first of all, I would like to consider mathematically such a vibrating or oscillating motion, which you can observe here. So we have a thread and a small body of mass m, and the thread length is L, and the body can be displaced and can take part in some oscillations, so that at some moment of time the body is here. What physics law describes this situation? Certainly we can use the second law and Newton's second law, because we have a body of mass m. At each moment of time this body has some acceleration because there are some forces acting on this body. So what forces act on this body? First of all, the gravity pull directed downward, and also there is a force of tension in the string. And we know very well that these two forces are directed, have such a direction and such a length that their vector sum is sure to be directed in this way so as to return this body to the original position. The body cannot jump up and fly somewhere, and it's not as heavy as to break the string. The body is sure to move in this plane and in this direction. So the net force acting on this body is sure to be directed here. And how to calculate this force? If this angle is alpha, then we have such a parallelogram with angle alpha here, and then this force F the net force acting on the ball will be mg sine alpha, because this is also angle alpha. And so we will have m, and a is the coordinate of this body if I measure it in this direction. Mx, 2 points, are its okay, let it be a coordinate equal to the force mg sine alpha, and sine alpha can be expressed as approximately this side, which is x, which is displacement divided by L. But if the displacement is positive, then the acceleration is negative, is directed in opposite. It will have opposite direction. So that here we will have minus mgx divided by L. M will cancel, and we will obtain an equation x 2 dots plus g divided by Lx equal to 0. So that this coefficient is sure to give us the square frequency, and the frequency of oscillations will be given by g divided by L, and the period of oscillations will be 2 pi divided by frequency. That will be 2 pi square root of g divided by L. What I have written here on the blackboard is valid under some strong assumption. This is not always true. This is true only if x is small. Because if x is not small, I will be unable to substitute x divided by L for sine alpha. Displacement divided by L will not be a sine alpha. If displacement, if x is large, that part of my derivation will be not true. The sine alpha can be expressed as small displacement divided by the length of this thread, x over L, only for small displacements. If displacement is large enough, then that will not be true. And if that condition will be broken, then the equation will not have this simple form. If I take into account the large displacements, then what is x? X is measured along horizontal axis, and so sine alpha will not be equal to x divided by L. That will be a different situation. So let's consider a large displacement. So this is the position of equilibrium, and I will consider a large displacement. This is the force of tension, and this is the force of gravity for a ball of mass m. As the ball will move in this direction, I would like to use now a different law of physics, which is also possible. I can use not only second Newton's law, I can use in this situation some other law of physics, which will be more appropriate, by the way, because this is a rotational motion, a part of rotation of a small ball about point O. And in any rotational motion, I can use the law of which describes the rate of change of angular momentum. So angular momentum, time derivative, equals total external torque acting on the rotating system. This law also can be used in this situation. What is angular momentum if the ball moves in this direction? That will be radius vector times momentum, vector product. And this radius vector, if you multiply it by momentum, the angular momentum will look perpendicular to the blackboard. And what is the external force? What is the external torque? Torque of external forces. The torque should be calculated with respect to this point. The force of tension will have no torque because its arm, the arm of this force, will be 0. But the force of gravity will have its torque because the arm of the force will not be 0. The arm of this force will be a shortest distance between the line along which the force acts and the axis of rotation. So that will be the arm of the force. That the arm of the force, this distance. So if this is L, the arm of the force may be denoted by A, for example. So that in this particular case, when the motion is a planar motion, I will have that the rate of change of angular momentum is moment of inertia of this body with respect to point A, omega dot equals the torque of external forces, and I have to take into account only the force of gravity, because this is the only force which will have a torque about axis O. So the force of gravity, mg, must be multiplied by its arm, A. And the arm can be calculated as, if this is angle alpha, as L sine alpha. L sine alpha. And the moment of inertia of small body about this axis of rotation will be ml squared by definition. So using all these equations, I will have ml squared, which is the moment of inertia. What is omega squared? Omega dot. Omega is the angular velocity of this ball in its rotational motion, and omega is somehow related to it will be angular acceleration. I will just leave it as that. Angular acceleration equals mgl sine alpha. M will cancel here. L will cancel. And angular acceleration can be written as alpha, second derivative of alpha. Second derivative of the angle of deflection will be angular acceleration in this motion. So I will have from this equation, well, also it's important to note that what about the sign of mgl? What about, should it be taken with plus or minus? Should it be taken with plus or minus? The situation is the same as with the body which was vibrating on a spring. If the deflection of the body is positive, then the force acting from the spring is negative. And if the deflection is negative, then the spring will be compressed, and it will push the body in the positive direction of x. So in this case, when the body is oscillating, the force acting on this body is always directed oppositely the displacement. For negative displacements, the force will be positive. And for positive displacements, the spring will be elongated and it will pull the body backward, and the force acting on it will be negative. So in this case, the force is always directed oppositely the displacement, so that the force acting on the body from the spring will be proportional to minus x with coefficient of stiffness, spring stiffness. The same situation is here. The same if you look at this vibrating ball, you will understand that here must be minus sign, because this moment, this torque of external force always returns the ball, always tends to return the ball backward. So the situation here is the same, and here must be minus sign. And from this equation, I will find that alpha, second derivative with respect to time, plus, when I take this to another side of the equality sign, then I will have plus alpha 2 dots, plus I will have to divide by L, so I will have G divided by L, by this L, sine alpha equal to 0. So this equation was derived without any approximations, without neglecting anything in this case. And instead of alpha, I have sine alpha. In this equation of harmonic oscillations, I have second derivative of x and x. And here I have second derivative of alpha and sine alpha. That's why this equation describes unharmonic oscillations. Unharmonic, the solution of this equation is not a harmonic function of sine or cosine. No, it's not a sine, no cosine. It's much more complicated. But for small alpha, that is, if alpha is much smaller than 1 radian, for small alpha, sine alpha approximately equals alpha. And then this equation will become an equation of harmonic oscillation. Second derivative of alpha plus g divided by L alpha. Instead of sine alpha, I put here alpha, because for small alpha, for small angles of deflection, that will be approximately correct, approximately true. It's correct for small angles. And this equation coincides with the equation for harmonic oscillations. So for small alpha, for small angles, this ideal pendulum will oscillate according to harmonic function, sine or cosine. Now the alpha can be considered small, and this kind of oscillation is harmonic. It's described by a harmonic function like sine omega t or cosine omega t. But if I choose to arrange an oscillation of this body at higher angles, at larger angles, yes, I have to keep it strong. At larger angles, when angle of deflection is comparable to 1 radian, it's not much smaller, then this oscillation looks like harmonic, but strictly speaking, it's unharmonic. It's described not by cosine function, but some similar function, but different from cosine. For example, if this is alpha as a function of time, cosine function is something like that. But when we have unharmonic oscillation, you will have here some other function which differs from cosine, Well, it's close. It can be approximated by cosine by harmonic function. But anyway, strictly speaking, it does not coincide. Actual displacement, actual angle alpha as a function of time will not coincide exactly with a harmonic function, because exact equation involves here sine alpha. After this preliminary remarks about the equation of harmonic oscillations, I would like to discuss the energy, the mechanical energy involved in oscillations. So when the body moves like this, mass vibrates here on the spring of stiffness K, we know the solution, we know the law of displacement as a function of time. So we know the kinetic energy. The kinetic energy of this body at any moment of time will be mass velocity squared over 2, and that will be mass. What is velocity? Velocity is the first derivative of this function. That will be minus a omega 0 sine. But when minus is squared, I obtain plus, so that will be a squared omega 0 squared sine squared omega 0 t divided by 2. That will be the kinetic energy of the vibrating body of mass m at any moment of time. What will be the potential energy? The potential energy, let it be denoted by U, for example. The potential energy of the spring is kx squared over 2. I would like to use the expression for k from this formula, so that k will be equal to omega squared m, or m omega squared. So instead of k, I will put m omega 0 squared. And x is known function, a cosine. And I have to take x squared. So I will have a squared cosine squared omega 0 2 divided by 2, omega 0 t divided by 2. Now if I consider total energy, which is kinetic energy plus potential energy in vibrational motion, I will have to add these two expressions, and that will be the same coefficient m a squared omega 0 squared, m a squared omega 0 squared divided by 2, and sine squared plus cosine squared. Sine squared plus cosine squared. What is this? This is always equal to unit. So that the total energy of vibration, of vibrational motion, will be given as m amplitude squared vibration frequency omega 0 squared over 2. That's the total energy, which remains constant in time. It does not depend on time. So this is independent of time. Therefore, it's constant, as it should be. Total energy is conserved because there are no forces of friction. no, only conservative forces are present here, the force from the spring, and the forces acting in vertical direction are compensated, they are cancelled, and there are no forces of friction, and therefore the energy of motion is conserved, and the total energy must remain constant. And that's why it will remain constant, because sine squared plus cosine squared is always a unit. If you look at the time dependence of all these functions, you will see something like that. What is sine squared? Sine squared is such a function etc. So the period is here. This is the period of oscillations from this point to this point. Because the sine itself, I will show it here. X as a function of t. X as a function of t is cosine, so I will show x dot as a function of t, the velocity as a function of t. The velocity will be sine as a function of t, and the velocity, if I take this derivative with respect to time, I will obtain minus sine a omega. So minus sine will be this function. That is the period. This point is period. So this is minus sine omega t. And if you square this function, if you take a square of each such number, negative number squared will give you positive number, and this will be the maximum positive number here, which corresponds to 1/4 of a period. And then at this point, the energy, the square, will be again 0, and at this point 0. And positive numbers squared will give you positive energy, as well as negative numbers squared will give you positive energy. So this is the kinetic energy as a function of time. This is the kinetic energy. This is the kinetic energy as a function of time. It's proportional to sine squared. What is the potential energy as a function of time? It's proportional to cosine squared. And if you consider cosine squared, that will be this function etc. So this is cosine squared, and this is potential energy as a function of time, which is proportional to cosine squared omega 0 t. So when you add sine and cosine at any moment of time, you will obtain the constant function, this constant function, which is the total energy, the sum of potential and kinetic energies. So in graphic representation, these formulas are very obvious and simple. This sine squared and cosine squared, if added, will give you a unity. Now I will derive a very important statement about the harmonic oscillations, important for the future. You will use this statement in your further studies next semester when you will study thermodynamics and molecular physics. You will need this simple statement, which I will derive now. I will find the average kinetic energy of vibrating body. The average kinetic energy or average value of any function is defined in this way. That is 1 over period, if this function is periodic, integral from 0 to period, this function k as a function of time dt. That is the definition of time average of any function. And I need to find an average value of kinetic energy. I have to take this integral for kinetic energy. So the coefficient there will be ma squared omega 0 squared divided by 2. And here I will have to take the integral of sine squared omega 0 t dt. Well, it's a very simple integral, but looking at the graph of this function sine squared, it's easy to understand that the integral, which is written here from 0 to capital T, which is the period of oscillations, this integral is this area under this curve, the area under this curve. So if I took the area of such a rectangular figure, it would be 1 times capital T. One side of the rectangular figure, 1 times capital T. But what is under the curve is just half of this. It's just half of this area, because another half is occupied by cosine. So this integral equals just 1/2. This integral equals just again, the area of this rectangular figure equals capital T, and the area under the sine squared equals capital T divided by 2. And I have to divide it by capital T, which is here as coefficient. So that will be just 1 over 2. So the final answer will be ma squared omega 0 squared divided by 4. That's the average kinetic energy of a body engaged in vibrational motion. Now I would like to calculate the average potential energy. This again is a function of time. I need to calculate the average of this periodic function. By definition, it will be 1 divided by period integral over the period from 0 to capital T, potential function as a potential energy as a function of time dt. And the same, I have to integrate this function. That will give me ma squared omega 0 squared divided by 2. And the integral for the same reason will be equal to 1 over 2, the same 1/2. So I will obtain again this quantity. The average kinetic energy and the average potential energy turn out to be equal. The average kinetic energy equals the average potential energy. And this is an important statement which will be used next semester when you will study molecular physics. And you should understand that this equation is true only for harmonic oscillations. Only for harmonic oscillations this is true. If your oscillatory system is unharmonic, then there will be some difference between average potential and average kinetic energy. Let's make a 5-minute interval. Okay, we continue discussing the energy of vibrational motion. And I would like to consider this equation for the total energy, which is constant in time, it's conserved. And I would like to consider what is kinetic energy. It's mv squared. And I would like to write this as m. Velocity v is the first derivative of coordinate mx dot squared divided by 2. And the potential energy is kx squared divided by 2. And all this is ma squared omega 0 squared divided by 2. So I will multiply this equation by 2 and divide it by m, so that the coefficient at the first derivative, at the first term here, will be unit. That will give me the following expression. After multiplying by 2 and dividing by m, I will obtain x dot squared plus k divided by mx squared equal whatever is there that will be a constant number which does not depend on time, a constant, because the total energy is conserved, so that the kinetic energy plus potential energy remains constant in time. We note that this coefficient exactly equals the omega 0 squared. So that from the energy considerations, I can obtain the following equation: x dot squared plus omega 0 squared x equals constant. This is another equation which applies to harmonic oscillations. Just compare this equation to this one. Here we had second derivative of x, and in this equation we have only first derivative of x, but squared. It's interesting because this equation was obtained from the Newton's second law. Mass times acceleration equal to force acting on the body from the spring. The second Newton's law allowed me to obtain this equation. But this equation was obtained from law of conservation of energy, mechanical energy. The first term refers to kinetic energy, and the second term refers to potential energy. Oh, certainly that must be x. Yeah, x squared, certainly. X squared. So I can treat the harmonic oscillations using the second Newton's law, which involves consideration of forces and analysis of forces, or I can use energy considerations. I can use kinetic and potential energy, and I can arrive at this equation, and what? Then I can see that this coefficient at the second term will give me the square of vibration frequency. So if I happen to write down the energy conservation equation, kinetic energy plus potential energy, in such a form that the coefficient at the first term is unit and the coefficient at the second form is anything, any expression, then I don't have to solve this. I don't have to solve this differential equation. I know beforehand that this equation is the square of frequency, of vibration frequency. So I can obtain vibration frequency either from energy consideration or from forces consideration and the second Newton's law. Whichever way is more suitable, I can use any way in solving any method in solving a particular problem. If it's more simple to consider forces and second Newton's law, I will arrive at this equation, and then I will find the frequency of oscillations. Or sometimes it's much easier to consider kinetic energy and potential energy. And if I happen to arrive at such an equation, then I will find the same, the frequency of oscillations, using two different approaches. Either approach based on forces or another approach based on energies. In any way, I can find this frequency. Let's consider some example, simple example. It's not very simple. It's very complicated. But it will be simple because energy consideration sometimes gives you a powerful tool to solve problems. Let's consider such a problem. Let it be a uniform disk of mass m and radius r. And this disk can roll without slipping. It can roll without slipping. And here, at this point, I will have a spring of stiffness K attached to vertical wall, and another spring here of stiffness 3K, anything attached to another wall. So if this system is in equilibrium, there are no oscillations. But if I somehow touch this disk, if I push it a little bit, then it will start vibrating. And vibration will include rolling. The disk will roll to and fro, and there will be some vibration with some frequency. How to find the frequency of vibrations? As an example of, this is an example of problem which can be solved much easier if you consider energy considerations, much easier than forces and torques and the equation of the rate of change of angular momentum. So it's possible to consider forces and torques of forces and angular momentum. How does it change? But actually, energy considerations will be much, much easier. Will give you directly lead you to this equation. The only problem here will be to choose coordinate x. What should be x in this problem? It may be angle of rotation. It may be deformation of one spring or the other spring, or it may be displacement of this point or this point. Well, you can use anything, but if you use some coordinate which is called a generalized coordinate, in this case, if you use, for example, angle of rotation, then you will have to express both the kinetic energy and the potential energy through the same angle of rotation. Or if you choose to use by x a displacement of this point of point O will move to and fro, and there will be a displacement of this point while the disk rotates and moves to and fro in its vibrational motion. You can choose the displacement of this point, because when the disk rolls, this point moves horizontally, parallel to the floor. So the displacement of this center of mass may be chosen as x, and then using this coordinate, you will have to find both the kinetic energy and the potential energy. And for both kinetic and potential energies, you will have to use the same coordinate. Whatever expression for potential energy you will have to use, you will have somehow to express the potential energy and kinetic energy using the same coordinate x. That's the only difficulty in this problem, the geometrical difficulty. It's not physics, actually. It's geometry. So if this point was displaced by some small distance x, then this point is displaced by 2x. And therefore, one spring will be deformed by 2x and another spring also by 2x. And so that the potential energy of springs will be what? K divided by 2, displacement 2x squared, plus the potential energy of the second spring, which will be 3k divided by 2, and again the same displacement 2x squared, which is the same for both springs. But if the second spring was attached to another point, for example, I could have attached the second spring to this point, then the displacement here would be different. Or the second spring could have been attached to this point. Then the displacement of this point would be different. But in this particular case, displacements are elongation of one spring equals the compression of another spring. So the potential energy will be given as 2x squared. This is 4x squared divided by 2. That will be 2x squared. And that will be equal to k plus 3k. That is 4k times 2, 8kx squared. That seems to be the potential energy. Now, kinetic energy. Kinetic energy of the moving disk will consist of two parts: the energy of motion of the center of mass and the kinetic energy of rotational motion, because the disk both rotates and moves translationary, that is, rolls in such a way that its center of mass moves. So that the kinetic energy of this disk will have two parts. First, the kinetic energy of motion of the center of mass. Mass divided by 2, velocity squared. Velocity is x dot squared. That is the kinetic energy associated with the motion of the center of mass, plus the kinetic energy associated with rotational motion. Rotational motion with respect to point O, to the center of mass. That will be moment of inertia about the center of mass O over 2 omega squared. And omega is the angular velocity of this disk. And the angular velocity can be expressed using the radius and x, so that x dot, the velocity for the center of mass, will be radius omega, angular velocity. And from here I can obtain m divided by 2 x dot squared. Why do I need this equation? In order to have both terms dependent on the same variable. I have chosen x to be the main variable in this equation, which is my purpose. My purpose is to obtain this equation for the energy conservation law. And here is the same coordinate, x dot and x. So I must use the same coordinate here to express all the terms in my kinetic and potential energy. Everything should be expressed using x and x dot and nothing more, no more angles, no more velocities, but just x. So I need to express omega using x dot. That will be x dot divided by r capital. So, and the moment of inertia of the disk is mr squared divided by 2, and then divided by 2 again. This 2 and omega will be x dot squared divided by r squared, that is omega squared. And from here I find that r squared cancels, and I will have mx dot squared 1 over 2 plus 1 over 4. That will be what? 3 over 4 mx dot squared. That's the total kinetic energy, and that's the total potential energy. So that's a law of conservation of energy will be kinetic energy plus potential energy. That will be 3 over 4 m x dot squared plus 8k x squared, and that is constant. And now one simple step remaining to obtain the frequency of oscillations in this oscillating system, mechanical vibrating system. The frequency can be found as the square root, according to all previous deliberations using this expression. So I have to, in order to obtain this equation, I have to divide my equation by this coefficient 3m divided by 4. 3m over 4. I have to divide everything by this coefficient so that the coefficient at the x dot is unit. And when I divide by this coefficient, the second coefficient will be equal to omega squared, frequency squared. So the frequency will be obtained immediately from here as the square root of 8k divided by the first coefficient, which is 3am, divided by 4, and 4 will come here. So the frequency will be 8 times 4, 32 k divided by 3m. That's the final answer. So we have found the frequency of oscillations or vibrational motion, oscillatory motion, in this complicated mechanical system when there are two springs and a uniform disk rolling without slipping, rolling without slipping. And it turns out that it's not very difficult to find the frequency of such oscillations, because we have a theoretical result which shows that the law of conservation of energy written in this form allows one to immediately find the frequency of vibrations as the coefficient at the second term in this equation. That's all. I just have to write down the law of conservation of energy, kinetic plus potential, and the coefficient at the second term. That's all. That's all there is to it. I don't have to solve differential equations. I just have to find potential energy and kinetic energy. And will the problem be much more complicated if this spring was attached to the middle of the radius here? Will it be much more complicated? No, because this point displacement will be very simply related to the displacement of the upper point as the displacement of upper point divided by 4 multiplied by 3. So the displacement of this spring here would be x divided by 2 multiplied by 3. So that will be 3x divided by 2 squared. So I will have to use this expression instead of this one if the spring was attached to this point. Is it difficult? No, absolutely not. Solution will be the same amount of efforts and time, and the frequency will be slightly different. But the mechanical problem, which seems to be complicated, two different springs attached at two different points to a body which makes complicated motion, but the solution is very simple because we use the law of conservation of energy, and the preliminary result, very important result, that this coefficient immediately gives you the square of vibration frequency. So, as an example, I gave you a solution of this problem which illustrates application of this important law of conservation of energy, which gives you immediately the vibration frequency. Now we go further, and then I have to consider, I will consider a physical pendulum, So far we considered mathematical pendulum, or mathematical or ideal pendulum, which is a small ball on a string. We considered this. And now I will consider arbitrary body, which can also be hanged on some point, and there will be an axis of rotation, and there will be vibrational or oscillatory motion of this body. So we consider the general case of oscillation of arbitrary solid body. So let there be an arbitrary solid body which is hanged by point O, so that it can oscillate as a pendulum, as a physical pendulum. Such an arbitrary solid body which has some axis of rotation about which it can rotate and oscillate is called a physical pendulum. Physical pendulum must have somewhere its center of mass, and the gravity force is applied to the center of mass, mg, where m is the mass of this body. And let this be a distance from the point of suspension point O, and the center of mass. Let there be distance L between these 2 points. And let there be some vertical direction. And when the center of mass is just below point O, the point of suspension, then the body will be in equilibrium at rest. It may be at rest. It may hang just without any vibrations. But if I deflect this body and let it return back, it will vibrate in such a way that the moment of inertia of this body about point O times angular acceleration of this body, which is alpha 2 points, 2 dots, second derivative, will be equal to, well, you recognize the equation. The rate of change of angular momentum must be equal to external torque, and the external torque, okay, let it be m, and the m will be equal to the arm of the force times the force of gravity, mg, times this arm of the force a. Arm of the force, I remind you, I recall that this is a shortest distance between the line along which the force acts and the axis of rotation. So this is the arm of the force, and this is here, and the arm of the force is equal L sine alpha. So that the torque will be equal to force mg times the arm of the force, which is L sine alpha, so that I will obtain an equation. And again, yes, that will be minus sine, because when the body is deflected to the right, as it is shown on the blackboard, the angle is positive and sine alpha is positive, but the acceleration will be negative. It will be accelerated in opposite direction. So that I alpha 2 dots plus mg L sine alpha equals 0. That's the result obtained from the law of change, of rate of change of angular momentum. Again, we note that this is an equation of unharmonic oscillations because there is sine alpha instead of alpha. To obtain harmonic oscillations, we must have here alpha. But instead of alpha, we have sine alpha. It means that the solution of this equation does not coincide with harmonic function. A harmonic function is either sine or cosine. Physically, it's the same. But for small angles alpha, sine alpha approximately equals alpha for small angles. And for small angles, I will obtain an equation of harmonic oscillations, which will take the form alpha 2 dots plus mgl, and I divide it by moment of inertia with respect to point O, moment of inertia about the axis of rotation, alpha equals 0. I know, and you know, now you know also that this coefficient equals the frequency of vibrations, or frequency of oscillation squared, so that the frequency is given by mgl divided by moment of inertia. And you remember that the frequency of mathematical pendulum of a small ball on a long thread, that frequency of vibration was equal to G over L. So there must be such an ideal pendulum which has the same frequency as this physical pendulum. In this case, the two frequencies will be the same, but L will be different. Here, L is the distance from the point of suspension to the center of mass. And here, that will be some different L, which I will call a reduced L. That is the length of ideal pendulum, whose frequency is the same as the frequency of physical pendulum. From here, I can obtain that the length of an ideal pendulum, LR, will be equal to moment of inertia divided by m L, because G will cancel in this equality, divided by ml. So if I have a physical pendulum whose center of mass distance from the axis of rotation is L, then the period of vibration of this pendulum will be the same as the period of vibration of ideal pendulum. A physical pendulum will have the same period and the same frequency as this such ideal pendulum, whose length is given by this formula. So I will indicate here the length, that reduced length, for example, Z1, that will be the reduced length, that section. The length of some ideal pendulum which will have the same frequency of oscillations. There must be some length, and it should be given by, it's given by this formula. And this point will be denoted by O prime. And there is an interesting theorem by Higgins. Higgins theorem. You know the Higgins-Steiner theorem, but this is only Higgins theorem, which says that if we take a physical pendulum and suspended it by point O and measure the frequency of vibrations, and then suspend the same physical pendulum by point O prime, then the frequency will be the same. The frequency of vibration and the period of oscillations will be the same. Either you suspend it by point O prime or by point AO. The period of oscillations will be the same. If these 2 points, if the distance between these 2 points of suspension equals the reduced length, which is given by this formula. That is a Higgins theorem. So, according to this formula, the reduced length is moment of inertia with respect to point O divided by ml, where L is the distance between the point of suspension O and the center of mass. According to the Higgins-Steiner theorem, moment of inertia about point O can be expressed as the moment of inertia about the center of mass plus m L squared divided by ml. So that will be the moment of inertia about the center of mass ml plus another term here, m will cancel, plus L. Now I will suspend this body by point O prime. And I will calculate the length of ideal pendulum with respect to this point O prime if the pendulum is suspended by point O prime. The length will be what? The length of reduced ideal pendulum will be what? It will be the moment of inertia about axis O prime. If this body is suspended by point O prime, then I have to calculate the moment of inertia about this axis O prime divided by m, and here must be the distance from O prime to the center of mass. Let it be L prime. According to the major formula for the reduced length, here must be the distance from the point of suspension to the center of mass. Let it be L prime. So this is the distance L prime, and that was the distance L, which can be expressed again using the Higgins-Steiner theorem as the moment of inertia with respect to the center of mass plus ml prime squared divided by ml prime, which is moment of inertia with respect to the center of mass, and that will be divided by ml prime plus L prime. And also I can see That's the length of reduced ideal pendulum equals L plus L prime, L plus L prime. Therefore, L prime equals the length of reduced pendulum minus L. And I will use this expression here. And the length of reduced is given by this formula, which I'll immediately use here. That will be I0 divided by ML and minus L. So I have used the formula for the reduced length of an ideal pendulum. So after substituting this expression into this formula, I will substitute both in this denominator and here. I will obtain the moment of inertia with respect to the center of mass, m multiplied by L prime, which is moment of inertia IO divided by ML minus L, and here plus L prime, which is which is what? L prime is, I don't see from here, I0 over L, I0 divided by ML minus L. Is that true? It's always difficult to have formulas written far from one another. Yeah. Well, so if you take into account, finally, I will not waste my time now. If you take into account this obvious result and this preliminary result and this obvious relationship between LR and 2L and L prime, you will obtain the result which I will just indicate here as the final result of the theorem. That's the reduced length calculated with respect to point O. If the pendulum is suspended by point O, that one will equal the reduced length calculated if the physical pendulum is suspended by point O prime. So whether you suspend it by O or by point O prime, the period of oscillation will be the same, because the length of reduced pendulum will be the same. Do we have another 2 minutes? Or okay. So, Дима, давай покажем вот этот. So here we have a physical pendulum and the ideal pendulum with reduced length. They have the same period of oscillation. So if I start oscillations, you see that the small white ball oscillates at the same frequency with the same period as this physical pendulum. They oscillate together. Though the small ball can oscillate, can move easily by itself. It's not attached to the physical pendulum. So if we change the 2 points, point O and point O prime, if we suspend the physical pendulum by point O prime, then the period of oscillation must be the same, because the reduced length calculated with respect to the new point of suspension equals the reduced length calculated with respect to the original point of suspension. We have 2 points of suspension, O and O prime. And for both points of suspension, we can calculate the reduced length according to this formula. And the reduced length is the length of an ideal pendulum which has the same oscillation period as the physical pendulum. So the same ideal pendulum gives you its own period of oscillation, and it turns out to be the same period of oscillation for the physical pendulum, whether we suspend the physical pendulum by point O or by point O prime. That's it. That's an experiment which illustrates, yes, it's better to keep it here. That's an experiment that illustrates the Higgins theorem. And the Higgins theorem, I repeat, is based on 3 simple facts. First, the reduced length equals L plus L prime. The distance from L is the distance from the center of mass to the first axis of rotation, and L prime is the distance from the center of mass to the second axis of rotation, which will be used later. So L, the reduced length, equals the sum of these 2 sections. And also, we use the expression for the reduced length calculated with respect to point O and point O prime. And we use the Huygens-Steiner theorem here in order to use the moment of inertia with respect to the center of mass. So 3 ideas, 3 equations will give you this result, that actually the periods of oscillation will be the same at whatever point of suspension you use here. So if we suspend the physical pendulum by point O prime, then the reduced length will be here. And if we suspend it by point O, which has the distance from point O prime equal to the reduced length of ideal pendulum, then the period of oscillation is the same. So that's the Higgins theorem and experimental demonstration of this theorem. Okay, let's finish on this point, because we had already the bell at the end of this lecture.